Okay, so welcome to Math Methods 2. So we're going to use a strategy similar to Math Methods 1, where we broke down the overall material into lots of small units. So for ease of organization, both from our point of view and also for ease of study from the student's point of view. So the first topic that we're going to cover is going to be about complex analysis, in which we will begin with just complex numbers in this lecture, and maybe a few more lectures we will just recall properties of complex numbers that we are all mostly expected to be familiar with. So in this lecture we will just start with some very basic definitions. That's what this lecture is about. Okay, so we can think of a complex number as essentially an ordered pair of two real variables, right? So there is a what we call x and what we call y, or also known as the real part and the imaginary part, right? So although this is somewhat more abstract way of introducing the notion of a complex number compared to how we might have first encountered it. Yeah, so usually we come across a complex number when we are trying to solve for certain algebraic equations, and we see that within the real set, it's not possible to find solutions for certain kinds of algebraic equations. And so the theory tells us that algebraic equations are guaranteed to have solutions if you go to complex numbers. We first start with natural numbers, then we extend to include negative numbers because certain equations don't have solutions with positive numbers. Then we extend it to real numbers, and finally to complex numbers, and that's it. You don't need to go beyond complex numbers. That's what the theory is. But it's also possible to think of a complex number as is made up of two real numbers, and it's an ordered set. So it's important to identify one of them as the real part and the other one is the imaginary part. And so so a number of the form x comma 0, if it has no imaginary part, then that's just a real number that we are more familiar with. We have used for a very long time. So just real numbers, but also the notion of I, the imaginary unit, is also quite familiar, where if there is no real part but there's only an imaginary part, and that imaginary part with magnitude 1, right? So it is customary to call x as the real part of z and y as the imaginary part of z, denoted as re of z and in of z. So the addition of two complex numbers is defined as simply adding the real parts and the imaginary parts. Two complex numbers, each of them contains these two pieces of information, and the different pieces of information add separately. So z is equal to z1 plus z2 means that its real part is going to be x1 plus x2, and imaginary part is going to be y1 plus y2. And so multiplication of two complex numbers is defined by this operation, right? So you take the the real part of the first complex number and multiply it by the real part of the second complex number, and then subtract the product of the imaginary parts of the two complex numbers. So if you're trying to multiply z1 times z2, so the real part of the resulting complex number, right? So we just have to specify the real part and the imaginary part of the resulting complex number, and so the real part is going to be given by just the product of the real parts of the two complex numbers minus the product of the imaginary parts of the two complex numbers which are being multiplied. And so the imaginary part is given by, of the resulting complex number, is given by the sum of the products of the real and imaginary parts. So you have x1 times y2 plus y1 times x2, right? So this is also something we have used. So but the thing is that starting from this definition, we can actually derive the identity I squared is equal to minus 1, right? So often we have probably encountered I as a solution to the algebraic equation, z squared plus 1 is equal to 0, and then we just simply introduce a label called I And so that's supposed to be the root of this algebraic equation for which there is no solution in real numbers. And so of course we know that I squared equal to -1 because that's often the starting point where we have encountered this. But you can actually derive this using this, thinking of it in an axiomatic way like here. So if you define multiplication of two complex numbers like here, and the imaginary I is defined as 0, 1, right? So I squared is nothing but the product of these two complex numbers, 0, 1 times 0, 1, and then we have this definition of product of two complex numbers. So you have to do 0 times 0 minus 1 times 1, and 1 times 1 times 0 plus 0 times 1, which is just -1, 0. And often if it's just a real number, you omit writing the 0 and you just identify it as just -1. That's a real number, right? So it is possible to build this framework up in an axiomatic way, and so we will not push this too far, but I'm just recalling a set of definitions, and we'll state certain properties and use these properties and get going in an intuitive way, right? So it is possible to spend a lot of time and do it in a very thorough, rigorous way, and there are math textbooks available where you can look up this way of building the whole structure. Okay, some more definitions and some basic properties. Again, stuff which we should be familiar with. So the complex conjugate of a complex number is another complex number, right, which also has a real part and an imaginary part. You just have to specify these two to specify a complex number. And here the real part of this complex conjugate remains unchanged, and the imaginary part has a change of sign. So x comma minus y, right? So z star is another complex number, and so we will see how the complex conjugate has makes a reappearance later on when we are studying the theory of analytic functions and so on. But even otherwise, so just as when simple operations involving complex numbers are involved, so this has great utility, right? So the notion of a complex conjugate of a complex number. So the product of z with z star is real, right? And as can be verified from first principles if you want by invoking the definition of multiplication. And so you can check that in fact z times z star is nothing but x squared plus y squared, or the sum of the squares of the imaginary and the real part of the complex number, right? So, and of course the complex conjugate of the complex conjugate of a complex number is itself, right? So because minus y, you get a minus 2 times, and then you return to the original complex number itself. So the magnitude or the modulus of a complex number can be defined using the complex conjugate. So it is written like here: mod of z is just the square root of z times z star, right? So we are guaranteed that the product of a complex number with its complex conjugate is not only real, but it's also positive, because you have the sum of two positive numbers, x squared plus y squared. So the square root of this quantity is definitely well defined. It's a real number, and it's the positive square root that you're looking at. So, and it's a non-negative quantity, a real quantity, mod of z, right? And it's the magnitude of a complex number z, which is defined as the square root of the sum of the squares of the real and imaginary parts of the complex number. So the division of two complex numbers, is something which basically follows from the definition of multiplication. So z1 divided by z2, can be written as z1 times z2 star divided by you just multiply and divide throughout by z2 star, and then make use of the fact that the denominator now becomes a real number. So then it's just like a multiplication of two complex numbers, z1 times z2 star, right? So this this property and similar properties where there are tricks associated with the modulus, and it has great utility. Now, a complex number can also be written in polar form, right? So the real part can be thought of as r times cosine of theta, and the imaginary part can be thought of as r times sine theta, where this r is actually nothing but the modulus of the complex number. And so there is a modulus of the complex number, and then there is theta is the argument of a complex number. So there is this geometric representation possible for a complex number. You can think of it as, essentially a vector in the two-dimensional plane, and then so theta is the amount by which your vector has rotated with respect to the x-axis. So the x-axis is nothing but the real axis, and the y-axis plays the role of the imaginary axis. And so this modulus of z is the same as the radius of this, the vector corresponding to the complex number that you're thinking about. And so you can basically write down your complex number z as r times cos theta plus I times r sin theta. So because the real part is just r cos theta and the imaginary part is r sin theta. So given a complex number in polar form, we can go ahead and expand the cosine and sine functions in a Taylor series, right? So each of them separately into Taylor series, and so cosine theta has this expansion 1 minus theta squared by 2 factorial plus theta to the 4 by 4 factorial minus, and so on. And likewise sine theta has this Taylor series expansion theta minus theta cube over 3 factorial plus theta to the 5 over 5 factorial, so on, right? You carefully collect these terms together, and then you have, you see that you have a 1 and then plus I theta, and then minus theta squared by 2 factorial can be written as I theta the whole squared divided by 2 factorial, because we know that I squared is minus 1. And likewise, we can write down minus theta cube by 3 factorial times I can be written as I theta the whole cube divided by 3 factorial, because I squared will give you minus 1 and I remains as it is. So this minus sign is taken care of. Then we write down the fourth term as I times theta to the whole power 4 divided by 4 factorial, because I to the power of 4 is just 1, right? And so likewise, so you can check that indeed all of these terms become positive if we bring in this I, and place it, in this strategic manner, and then we collect terms together to write down this one common series. And then we see that this series is nothing but the series expansion for the exponential. So in fact, we identify that z is equal to r times e to the I theta. So this function cos theta plus I sin theta is actually nothing but e to the I theta. So this is this is not a completely rigorous derivation, but this is an argument if you wish. And so this goes back to Euler. So this identification of this exponential I theta as cosine theta plus I sin theta. So the real part of e to the I theta is just cos theta, and the imaginary part of e to the I theta is sin theta. And so this equation, is extremely convenient. It allows us to prove all kinds of remarkable results. And so one particular very beautiful result which immediately follows from this is when you put theta equal to pi. If you put theta equal to pi, we have e to the I pi is equal to cos pi we know is just minus 1, and sine pi is 0. So if you collect terms, so then you get 1 plus e to the I pi is equal to 0. So we have cos pi is minus 1. So minus 1 you bring to the other side, and then so I times sin pi is 0. So indeed, so now you see that this equation has 1, it has e, it has pi, it has I, and it has 0. These are all the fundamental constants of mathematics. All 5 of them together appear in this very beautiful equation. I guess this equation also goes back to Euler. It's one of those remarkable and celebrated equations. So the argument of a complex number is this thing called theta, and which there is this notation for the argument of a complex number, and it is just written as argument of z, and it can be thought of as just tan inverse of y over x, right? So because you have this the real part is cos theta and the imaginary part is sin theta. I mean, there is an overall magnitude as well, and so these will cancel out, and so it's just going to be tan inverse of y by x, right? So that's where, so you can write an expression for cos theta and for sin theta, and then divide y by x and then show that indeed tan theta is just y by x, right? So therefore you get this expression. And so the key point to note here is that this theta is not unique, right? It has in fact infinitely many different values, and they all differ by integer multiples of 2 pi. So tan inverse is this function arg of z is sometimes also called a multi-valued function. So so there is a way to make this get a unique value, and that is to restrict your answer to lie within a range. And so the standard range that is taken is minus pi to plus pi. So if you restrict the argument to lie within this range minus pi to plus pi, then the function is denoted with the capital A. So this arg of z is just so we have this small arg plus 2n pi. So indeed, so this capital arg has to be fixed in such a way that so in fact it actually makes more sense to write it in this manner. So the small arg is equal to capital arg of z plus 2n pi, right? So arg of z is there's one value for capital arg of z, but there are all these infinitely many different values that are associated with small arg, right? So this notion of non-uniqueness is something which has consequences, and then perhaps much later we might return to this this aspect of complex functions which don't have a unique value. Now the product of the magnitudes of two complex numbers is simply the magnitude of the products. Very straightforward. Mod of z1 times z2 is just mod of z1 times mod of z2. And when two complex numbers are multiplied, their arguments add, right? So this is the small arg. You should be careful. Capital arg may not add, because this restriction sometimes it does not quite add. Although if z1 and z2 are of a certain special kind, or there are arguments are certain values, this equation may hold. But in general, capital arg of z1 times z2 is not equal to capital arg of z1 plus capital arg of z2. But this is true, right? This equation does indeed hold, right? I mean, we should always allow for the fact that each of these args comes with a is modulo some free multiple of 2 pi, right? So within that extra freedom, this equation certainly holds. So the small arg is there is an extra freedom which can always be exploited, and so this equation does indeed hold. Okay, so most of the material that we have covered in this lecture are probably already known to all of us, but so therefore this must be thought of as in the nature of recall, and we will start using some of these properties starting from the next lecture. Thank you.